Okay, in this lecture we're going to talk about a method by which we can actually divide a polynomial into another polynomial. Now you remember that doing long division, for example, if I had 1,256 and I divide it by, say, um, 18, all right, then we would normally just say, well, let's do a long division here. 18, 1, 2, 5, 6. Into 1 doesn't go, 12 doesn't go. So how many times does it go into 125? Then that would be 6 and 6 and 48 would be 108. So 108 and 18 would be 126. So that means we need to go 6 times, which is 108. When we take this off, of course, we get 7 and we get 17. Then we'd bring down the 6, right, and of course we'd have a 6 here. And then we're looking for 176. Well, it wouldn't be a 10, so it would be 9. And 9 would be 162. And when you subtract that, you would end up with 414. So really what I have here is that 1256 divided by 18 is actually equal to 69, and it would be plus 14 remainder. Okay, and that remainder we'd write as 14 over 18. Okay, which of course we'd cancel down to 7 or 9. Okay, so you'll see here then that with our long division we ended up with remainder. Now, how I want you to think about the division algorithm is like this. If I divide f by g of x, I actually get another polynomial, just like I've got another number here, plus a remainder, and that remainder, here it is here, was divided by what we divided by, like so. And if I multiply everything through by g of x, then I end up with this thing here. So this is just a way of doing the same thing as what we did with numbers, except we're doing it with polynomials. Okay, right, now the synthetic division process is going to help us do a long division, which with a much easier process. Because normally what we did with the long division for polynomials was we said, all right, well, let's put our 4x cubed in here minus 15x squared plus 11x minus 10, making sure all the terms are there. We said, what do we multiply x by to get 4x cubed? Well, it was 4x squared, and we'd get 4x cubed here minus 12x squared, and then we would subtract. And that would give us 0 here, and this would be negative 15 plus 12 is negative 3x squared. We bring the 11 down. So what do we get? How do we get a negative 3x squared? Well, we'd never need a negative 3x. Okay, and then we'd bring the negative 3x squared down here, plus 9x, and we subtract. Again, we get 0 here, and we get 11, subtract 9 is 2x, and we bring the negative 10 down here. Then we'd have to multiply this by 2, okay, and we'd end up with 2x minus 6, and when we subtracted, we get 0 here, and we'd have negative 4 here. And this was the remainder. So in other words, what I'd have here is this, is that this particular polynomial is equal to this polynomial times this polynomial with a remainder of negative 4. Okay, so up here what I'd have is 4x cubed minus 15x squared plus 11x minus 10 is equal to x minus 3 by 4x squared minus 3x plus 2, and subtract 4. So that's the division algorithm. Now, to actually do this question a little easier, what we do is we use a synthetic division process, and this is the way it works. We first of all make a symbol like this, and instead of x's, I'm going to use the opposite of the -3, because I'm going to keep everything as an addition. Notice this was all subtraction here. I'm going to keep everything as an addition, so I'm going to use a 3 here. I'm now going to use just the coefficients of each term, like so. Okay, the first step is to bring the 4 down. Then I go 3 times 4 is 12, and I add, and I get -3. Then I go 3 times -3 gives me -9, I add, I get 2. Now I go 3 times 2 is 6, and I add, and I get -4. Notice I get exactly the same thing here, 4, -3, 2, 4, -3, 2. So this is telling me that this particular division produces 4x squared minus 3x plus 2 with a -4 over x take 3 as a result. And if I write it as a division algorithm then the top one is actually equal to, notice we have the same thing, g, which of course is our polynomial we're dividing by, our result, which is q, often called the quotient polynomial, and then subtract 4, and we get exactly the same result, but there's a lot less work involved. Now, a good application of this is what's called the remainder theorem, in that if you look at this one up here again, if I now look at, let's suppose I take k is 3 here, like we had up in this first example. Well, f of 3, if you actually work it out using the polynomial, I'd have 4 by 3 cubed minus 15 by 3 squared, right, plus 11 by 3 minus 10 comes out to be 4 times 3 3s are 9, 27, minus 15 by 9 plus 33 minus 10. Now when you actually work this out, you'll end up that you have 28, 108 there by the look of it. Yeah, 108. This one will be 9, 135 plus 33 minus 10. Okay, now when you actually do this, all right, you'll end up with -4. And notice that was exactly the remainder. So the remainder theorem says, all right, that if I divide my polynomial by x minus k, then that actually produces a remainder of f of k, whatever the value of that is. All right, now, how do we use this? Well, let's use the remainder theorem here to find f of 4. You can see here the calculation gets a bit tedious, so what we can do, and plus the fact we're going to be able to use this result later if we do it this way. And that is this. So again, let's put all of our coefficients, 4, 3, oh, there's no squared, so we need to put a 0 there, okay, and a -50 and a 25. There's a common error here is to leave that one out. Notice there's no x squared term. And we want to find f of 4. So let's put 4 in here. And, oops, 4. Okay, now, bring the -3 down. Okay, so we go -12, add, we get 3. We get 12, we add, we get 12. Here we get 48. Add, and we get -2. Multiply, we get -8. And of course, here's our remainder, so I'll take 8 off of here, so that will give me 17. Okay, and so consequently we see that in this particular case, we're going to actually get a remainder here of 17. So this is the remainder. So I can clearly say by the remainder theorem that this is equal to 17. Right, so that's how we use the remainder theorem. Now, a natural consequence of that is to find out whether or not a value is a zero, because if the remainder is equal to zero, then we know that this polynomial divides exactly into the other polynomial. Right, g of x divides exactly into the f of x polynomial. And so, right, this x minus k, right, or rather this k is a factor. I should say a zero. And this will lead to x minus k being a factor, which we're going to talk about as a factor theorem next. All right, so let's have a look and decide whether k equals 2 is in fact a zero. To get it to be a zero, I'm looking for a remainder of zero. If I don't get a remainder of zero, all right, then of course this is not a zero. So in this case up here, for example, all right, 4 is not a zero. Why? Because, right, this was not equal to zero. Right, well, let's look at this one. So again, we set this up. So we have a coefficient of 2 for x cubed, negative 3 for x squared, or we don't have an x, so we'll put a 0, and a negative 18. Right, and of course we're looking for k being 2, so let's put the 2 there. Bring the 2 down, 2 2s are 4, add, we get 1, 2 1s are 2, add, I get 2, 2 2s are 4, add, and I get negative 14, which is not equal to 0. So k equals 2 is not a 0. Okay. All right. So that's how we do. That kind of question. And of course, the things to look for here, okay, is number one, make sure you know how to do the synthetic division process. Number two, the remainder theorem. So we actually, when we do the synthetic division process, this remainder here is actually the value of the function at the value we're using to use the synthetic division. And if this remainder comes out to be 0, all right, then we say that this number is a 0 for this polynomial. And if it doesn't come out to 0, it is not.